everybody. I am going to go through a quick embryology review of our gastrointestinal tract for our upcoming midterm. Quick is relative. Let's see how long this actually takes. But let's dive right in. Okay, so I didn't have the time to draw everything out like I did in our last lecture from BMS 150. So I'm just going to be going mostly off the slides and supplementing where I can when I can. So we're going to start with a quick review. We didn't actually get this far, I don't think, in my last video. But we're looking at the development here of the mesoderm and sort of the structures that arise within that structure, because we went from our bilaminar disc to our trilaminar disc. So now we have ectoderm, mesoderm, and endoderm. Endoderm being on the inside, ectoderm being to the back or dorsal side, and then the mesoderm being in the middle. So the intraembryonic coelom is going to appear as an isolated space in the lateral mesoderm and the cardiogenic mesoderm. So that is going to be this portion here. This is our lateral mesoderm. These spaces are going to coalesce or join together to form a single horseshoe-shaped intraembryonic coelom. Now the intraembryonic coelom is right here. Essentially what happens is you have a congruent or like piece of tissue, the mesoderm, that's stuck together like this, or it's a singular unit of tissue. But with time, you sort of get this pocket forming in the middle as fluid starts to accumulate, and it separates the mesoderm into two separate layers. That's what this is illustrating right here. We see the fluid accumulating to form the intraembryonic coelom. To the dorsal side, the back side, which is here, because remember, this is our ectoderm, this is our endoderm. We've got the yolk sac, or primary umbilical vesicle, to the ventral side, and then above here, we've got the amniotic sac, or cavity, to the dorsal side. This is also where the spinal cord is developing, and then this down here is going to become more the ventral surface or the front of the embryo. As the intraembryonic coelom divides, the lateral mesoderm, again, only this part here, we are going to get the somatic or parietal layer. Now they're going to interchange these words a lot on our slide, so try and remember that they're one and the same thing. Somatic meaning body, or soma meaning body, which is going to be the more back layer. So that's this layer here. And then the front or ventral layer, this one here being the splanchnic or visceral layer. Now, I'm sure you've heard the term viscera, meaning sort of the abdominal cavity or the organs inside of us. If you're having a hard time remembering what viscera means, maybe you've heard the term eviscerated, like a medieval battle term, you know, when somebody basically eviscerates you, they cut you through the abdomen and anyway, a little bit morbid, but that's one way I remember visceral, being the viscera or the stomach or the organs of the body cavity, essentially. And then soma being body helps me remember it's sort of to the back and it's going to form the body cavity itself. So we've got three structures seen in the lateral mesoderm at this point: the somatopleur, which is again this part, the splanchnopleur, which is this part, and the intraembryonic coelom, the fluid cavity in the middle. The splanchnopleur is going to give rise to much of the, let's see if my pen is working. Sorry guys, my little laser pointer is not working, but that's okay. I'm just going to use pen instead. The splanchnopleur here is going to give rise to much of the embryonic gut tissue. So like the stomach, the gastrointestinal tract, the spleen, the liver, the pancreas, etc., which we're going to see as this lecture progresses. The intraembryonic coelom is between the two structures, as we've already seen, pretty repetitive. Now here, the intraembryonic coelom during the second month will develop into three main body cavities. So because this is already a cavity, aka a fluid-filled space, it makes sense that it's going to create new spaces within the body. We typically have three sacs or cavities within the abdomen. We've got our pericardial cavity, or the sac that contains the heart, the pleural cavity, or the sac that contains the lungs, and then the peritoneal cavity, which is sort of everything from the diaphragm down to the pelvic bowl. That's where all of our intestines lay. A lot of our other organs, like the liver, the spleen, and the pancreas, are all going to be in that peritoneal cavity, as well as some of the lower pelvic bowl, like your bladder and colon, etc. Um, the portion of the intraembryonic coelom that becomes each of those three cavities is really going to be dependent on its geographical location, if you will. The part that is more cephalad or to the head here, that's going to become the sac around the heart. The middle layer, you can zoom in here, sort of this segment here is going to become the peritoneal cavity, or sorry, what am I saying here? The pleural cavity. Um, so around the lung, and then this like more dorsal or caudal, caudal's more accurate, to the tail. It's not to the back, it's to the tail. The more caudal end is going to become the abdominal cavity. Here I have cephalad to the head, the middle area, and then to the butt, or to the tail, also known as caudal. Now, I remember really struggling with being like, how does this equal this? Like, what is this picture showing us? So I'm just going to quickly pull up for you guys my BMS 150 lecture and just quickly sidetrack just to explain how those two pictures relate to each other. Okay, I'm going to see if I can find a good picture. This is pretty good. So basically, this picture here is a cross section of, say, this region right here. So we have these little bumps and this valley, and then another bump, and then another valley. That's seen here. We've got our bump, our valley, our bump, our valley. Kind of that structure here. We're seeing that here. These little red things are the cardiac mesoderm, which are just little dots of random tissue that will become part of the blood supply and also the heart. Now here's the development of that intraembryonic coelom. I have it in purple just because I already have blue referencing the ectoderm, so I didn't use blue, even though this is a fluid-filled space. So if that makes more sense to you, you can think of it that way. But here we've got the somatic layer on the top and this splanchnic layer to the bottom. Here's another sort of, this would be like a mid-sagittal, no, sorry, this picture here is just this little segment, but zoomed out. So you're getting the entire picture so far of what's going on. We're still sort of looking at a transverse plane of the embryo in this image. Anyway, so this intraembryonic coelom, this space here, it starts initially as like little pockets randomly. So you may have a little bit developing here, a little bit developing here, a little bit developing here. And eventually those pockets of fluid all connect together to make this horseshoe shape. So if you were to see this picture and you'd imagine that you had a bit of the structure in front of and behind, you would see that purple image or the intraembryonic coelom like kind of coming out and around in this three-dimensional horseshoe shape. So hopefully that helps you get the picture of how those two images work together. Okay, yeah, there's the same picture, right? Like what I just had drawn for you guys, but this time from the textbook. So we have embryonic folding. I didn't go into this in our review, but it is really critical to sort of understand what's happening, how we get from a flat trilaminar disc to a three-dimensional embryo or baby eventually. So we have a tube, or we have a piece of paper. This is our trilaminar disc with neural tube developing on the front, on the back. This is going to be the amniotic cavity around this side. This would be the yolk sac down here. And basically what's happening is we have this sort of folding happening where the two ends, the head end and the tail end, are folding up to meet each other in the middle like this. So this is how we're going to end up getting our body cavity in the middle here. We're making a cavity for everything to start growing and filling into as the head and tail region come together. So we're getting folding from the head to the tail called cranial-caudal folding. But then we also have, if we unfold that, we also have the embryo folding this way as well. So if I turn this for you guys, it's folding along this dimension as well. It's kind of like, it's reminding me a little bit of like a bao bun. You know, you originally have this round disc and you're folding all the pieces towards the same central point. That central point that all the tissue is folding towards is going to become the umbilical cord. And we're going to see a little bit of the yolk sac there as well. So we've got our cranial-caudal folding and our lateral folding. That's what this is showing here. The head is folding in this way, the tail is folding in this way. And then if we flip the plane the other direction, we're seeing that the sides are folding in together as well here. So the amniotic cavity kind of starts originally like this around, but then if we turn it sideways, the amniotic cavity is coming down, 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 down like this, and it's slowly pinching this umbilical vesicle almost completely shut. It started as this big thing, but now because the amniotic cavity is folding laterally around the embryo, you're only getting this tiny little piece of tissue left that's actually connecting through the umbilical cord to the placenta and to the uterus lining, which is pretty crazy because you only have like half the amniotic cavity, or only half of the embryo up to this point has been around having an amniotic cavity, but now it's basically surrounding the entire baby, which makes sense for those of you who have thought about or have seen ultrasound images where you have this baby and it's really only connected to the mother via the umbilical cord. It's not stuck deep in the tissue like we've seen at this point anymore. Okay, the dates for this, we see folding start in third week, at the end of the third week, and it continues throughout week 4. As the folding happens cranially, the brain vesicles begin to appear and a few somites are obvious. So as this part is folding over, we see the primordial brain essentially. The mass is growing and growing and growing and growing. And it's gonna create those primitive vesicles of the brain, like the diencephalon, the mesencephalon, etc. Okay, so because we're focusing with this lecture on the gastrointestinal tract, we have to sort of understand how this folding is playing into the development of the abdominal cavity and thus the organs that we know reside there. So part of the endoderm of the umbilical vesicle is incorporated into the foregut. So as we see here, this is the primordial brain. It's folding down and inwards. So right here, oh, let me just get rid of that, make that better for you guys. We have the oropharyngeal membrane right in front of the brain. It's like, what? That's the mouth. Why is that in front of the brain when we know our brain now is on top here and our mouth is lower down? And we also have the heart. Like, what the heck? How is the heart above the brain? Because of the folding downwards, all this stuff is getting tucked down and below the brain here. So we see this part here getting tucked down and under and up right here. So what does it mean to say that the foregut is becoming incorporated into the embryo, but and is made of the endoderm? So the endoderm is this bottom layer of tissue here. Because we're getting this folding, this endoderm is sort of folded, forming a diverticulum or like a pouch. And this is going to become the mouth and then later on like the entire intestinal tract. One critical thing to conceptualize with this is we have to remember that our intestines are technically the outside of our body. I had someone explain it to me once, like taking a bagel. You have a bagel, but there's a hole in the middle. The hole in the middle isn't part of the bagel, it's part of the space around it. If you put a bagel next to a bagel next to a bagel, you end up with this big long tube through the center of these bagels. That's basically our intestines. They're technically the outside of our body because they make contact with the world. We have a mouth and we have an anus. Those are sort of like they're closures, but they're not a solid barrier of tissue. Things can pass in and out of both of those structures. So technically our insides, our intestines, are part of the outside of our body. I hope that makes sense because once I conceptualized that, it started to make way more sense with what's going on with how the foregut forms from endoderm, because the endoderm is the tissue that makes it the barrier between us and the outside world. So this is just saying the foregut lies here between the brain and the heart. So it's still the same thing as we experience folding. We have the brain and the heart, this is great. I love how we see that the heart is folding down and in, and it's becoming part of where the chest will arise from. Okay, the oropharyngeal membrane separates the foregut from the stomodeum. So the stomodeum is this space right here. This is basically going to become the mouth. So the stomodeum is just this part of the amniotic cavity that like is exposed to the rest of the amniotic cavity. It says here, this is the primordium of the mouth. So all of our mouth structures are going to develop here. Okay, the septum transversum lies caudal to the heart, which, after folding, it's caudal, it's to the tail end here. But initially, it's actually cephalad to the front, to the head, but with folding, it becomes caudal. This is going to become the central tendon of the diaphragm here. So this comes all the way down, it becomes even lower in the chest cavity towards the diaphragm. So that kind of makes sense why the septum transversum now is going to give rise to the central tendon of the diaphragm. This is also going to separate the abdominal cavity from the thoracic cavity. Okay, so that's what's happening at the front end. What's happening at the back end? So we've got another membrane, like the oropharyngeal membrane. It's got no mesoderm in it. It only has ectoderm and endoderm. It never became a trilaminar disc, if you will. It's the only part of the embryo that no mesoderm arises, because later on these are going to become openings. So there's no point in having a bunch of extra tissue in the middle. The caudal eminence, trying to find that here. That's just sort of this structure here. Projects over the cloacal membrane. Part of the endoderm germ layer is incorporated into the embryo as the hindgut. So this is the same concept as what we just saw at the front end, where we have endoderm forming like a kind of pouch or pocket as it folds, a diverticulum, if you will, and this is going to become hindgut. The connecting stalk is going to be attached eventually now to the surface of the embryo, and the allantois is going to be also sort of more incorporated into the embryo at this stage as well. So before, like this wasn't this is the baby or embryo. This is just the yolk sac below. We have the allantois. But now because everything is folded inward, we get all of the stuff incorporated into what will become the baby or the embryo. The connecting stalk is now attached to the front. I said that already, because remember the connecting stalk is going to be relevant in terms of the umbilical cord, how the baby stays connected to the placenta and the mother to receive nutrients. I'm just going to skip over lateral folding. Maybe I'll just hit some of these highlighted words here because I don't want to go too much in depth of what this looks like. We've already sort of covered that. Again, we see the endoderm incorporated now into the midgut. You know, if this was our trilaminar disc with, I'm just going to rotate it like this, with lateral folding like this, the bottom tissue being endoderm, the tissue on the back being ectoderm, we're getting this folding. So the endoderm, which was previously on the bottom, is now folded up to be part of the inside of the embryo. That's the midgut. So both foregut, hindgut, and midgut all come from endoderm. The foregut and the hindgut arise from head-tail folding, while the midgut arises from lateral folding. Initially, there is a wide connection between the midgut and the umbilical vesicle here. See how wide that is? But with time, that's going to shrink and shrink and shrink into this like tiny little connection here. And this will make a lot more sense too as we look at the gastrointestinal tract. Like what is the yolk sac or the umbilical vesicle at this point? Like it basically becomes nothing important. In fact, it's becoming so unimportant, it's getting pinched off and it's getting a new name. The connection that was previously the yolk sac is now called the omphaloenteric duct or the vitelline duct. And this is going to remain sort of inside the umbilical cord for quite some time before it eventually completely disappears and goes away. There is a remnant of this potentially in some people, which is going to result in Meckel's diverticulitis. Remember in diverticulitis, you get outpouchings of the large intestine, where it should be a smooth tube, but you get sort of a little outpouching or blob, where the hollow space in the middle sort of projects outward and you get a little bit of an outpouching. So that comes up right at the end of this lecture. Just remember, remnants of the omphaloenteric duct or the vitelline duct can give somebody an appendicitis-like presentation, but in the lower left quadrant of the abdomen instead of in the lower right quadrant. Just reading this over. The region of attachment of the amnion to the ventral surface of the embryo is also reduced to a relatively narrow umbilical region. So before, that's what this image is. Before we had our bilaminar disc, we had one bit of ectoderm to the amniotic side, endoderm to the yolk sac side or the ventral side. But what's happening is as this folds and becomes more of this structure, sort of we're starting to see the form of a fetus taking place. The amniotic sac sort of grows and grows and grows like this. And then we get this shape here. So really what it's saying that the region of attachment of the amnion, remember this is the tissue, the amniotic tissue layer filled with amniotic fluid around the baby. It's attached to the ventral surface of the embryo, but it's reduced to a very narrow region. So the only part, the tissue used to touch all of this part of the embryo. But at this point, it's not really touching any of this anymore. It's only connecting to the umbilical cord right now. only this really narrow part of the ventral surface of the embryo has any connection at all with the amniotic tissue. Okay, so I hope that makes sense for you guys. Um, okay, this image I drew out, it's pretty, once you see this image and you understand what each thing is, it'll make a lot more sense, but I'm gonna come back to that. So the ventral body wall is now complete except in the region of the connecting stalk. So that lateral folding is completely closed off except where the umbilical cord is. And the gut tube itself has formed. We have a complete tube. We can imagine that this seam is closed. So we have a tube now. It's completely closed off everywhere from the mouth primordium to the anus primordium, except in one region. If we looked at this piece of paper from the side, it's closed off everywhere except right in the middle. So there's still a little hole in the middle right here, but on either side it's closed. It's a complete tube. Which is what this is saying. It's completely closed except for connection from the midgut region to the yolk sac, which forms the vitelline duct, which again can be a remnant that doesn't completely disappear after the baby's born, and that can give us Meckel's diverticulite. Yeah, okay. I'm trying to think of like what is the relevance of this duct. In other creatures, it's suspected it could play a role in nutrient absorption from the umbilical arteries, but in humans, it doesn't really have a point. Okay, the serous membrane. Remember, serous and somatic mesoderm were the same thing. We're just seeing the word serous used now instead of somatic. And parietal, sorry. Actually, scratch out what I just said. The serous membranes, you know what? I'm not going to go into it because I don't know how to explain it properly. But we'll just go off the slides here and we'll see if we can work it out together. Oh, that's what I was trying to say. The parietal layer, so parietal and somatic mesoderm are the same thing. Visceral and splanchnic mesoderm are the same thing. That's, sorry, what I was trying to say. The serous membranes, I'm sure we know what those are. They're fluid secreting membranes that are going to help line the body cavities. So the somatic mesoderm, or the parietal layer of the lateral plate mesoderm, forms the serous membranes lining the outside of the peritoneal, pleural, and pericardial cavities, while the visceral layer of the mesoderm forms the visceral layer of the serous membranes, lining outside of the abdominal organs, lungs, and heart. So if we remember, let's just say let's just draw the heart. We have two layers of serous membranes. So if we have our heart, we've got a serous membrane that touches the heart like this. This is the visceral layer. But then within the context of the chest cavity, so this is the chest cavity itself, we can imagine we have lungs behind the heart, the stomach, the diaphragm, etc. We're also going to have a layer of serous membrane that lines the cavity itself. In this case, I'm actually going to erase that one because the heart has its own cavity. I'm just going to draw it like this. Sorry, I'm going to actually change my I'm not going to say the heart because it's too hard to conceptualize. I'm going to say we have our lungs. There's our lungs. Okay. So the lungs obviously sit in the chest cavity, but the visceral serous membrane is going to be the membrane that touches the lungs themselves. And then we're going to also have another membrane that touches the chest wall, essentially. There, that's a better example. And then in between these two layers, we have serous fluid, which if you guys remember, this is one of the things that maintains pressure between the lung and the chest wall so that as the lungs inflate and uninflate, the chest expands and shrinks instead of the lungs themselves separating from the chest wall. Okay, so the somatic mesoderm is going to be this outer layer here. The splanchnic mesoderm is the layer that touches the organ. So one touches the body cavity wall, one touches the organ directly. That's what this is saying down here. Okay, I gotta speed this up. We're only on slide 18. Okay, so the somatic and splanchnic layers are continuous with each other as the dorsal mesentery, which means like at the back of the body wall, these two membranes come together and they are continuous with each other. So now if we looked at the heart, now is a good one to do the heart, like this. Imagine we're looking at it from a bird's eye view. You've got layer 1, layer 2. So they are continuous with each other at the back. So this is the back, the front, or the ventral side, dorsal side. This ventral mesentery exists from the caudal foregut to the upper portion of the duodenum and results from the thinning of the mesoderm of the septum transversum, which remember was that structure that lies underneath the heart after we have cranial folding. Just going to stop screen sharing for a moment. I'm going to pause. Okay, I just had to take a second to reorient myself to the slides here because even I'm getting confused with all of this. But I'm doing my best to stay on top of it for you guys. Sorry, just trying to screen share. Here we go. Okay, so we're switching off of the serous membranes now, and we're going to look at the septum transversum. We briefly talked about that, and we're going to go a little bit into more detail here. So the septum transversum is a thick plate of mesoderm tissue. We've seen it already here. That occupies the space between the thoracic cavity and the stalk of the yolk sac. We already said that this is where the main ligament of the diaphragm is going to arise from, so that should be one way for you to integrate this knowledge. It is separating the chest from the abdomen. We see that the septum is derived from the splanchnic mesoderm surrounding the heart, so not the somatic mesoderm, which again is the body, and the splanchnic mesoderm being more the visceral or internal organ tissue. It's going to assume its position between the primitive thoracic and abdominal cavities where the cranial end of the embryo grows and curves into the fetal position. The septum does not separate the thoracic and abdominal cavities completely, but it does leave a large opening known as the pericardioperitoneal canals on each side of the foregut, which, sorry, my image here cuts that off, foregut. That's better illustrated here actually than in my picture. So this is a large opening here, and then behind that we have another large opening. Those are the pericardial canals. During further development, those pleuroperitoneal folds and the membranes grow medially, so they start at the posterior wall of the embryo, and they're growing medially towards the pericardio-peritoneal canal. So remember this hole right here is illustrated in this picture by this space right here. As they grow medially, they eventually fuse with the mesentery of the esophagus, and that forms the crura of the diaphragm around the aorta. Remember, the diaphragm has this like really tenting like structure, kind of like that. But we have three holes in it. We have a hole for the aorta, we have a hole for the esophagus, and we have a hole for the inferior vena cava, which we see here. Aorta, esophagus, inferior vena cava. So that's what this is saying. The diaphragm is fusing with the esophagus to form the crura of the diaphragm. The pleuroperitoneal membranes then grow until they fuse with each other and completely cover the septum transversum. Here. And I'm trying to find the septum transversum. Here. So you see that they started small, they're growing medially, then eventually they keep growing and they cover the septum transversum at all sides. And then we're going to obviously see the muscle growth in that region as well. To summarize, the diaphragm is derived from the following structures: two pleuroperitoneal membranes, these membranes here, that cover the septum transversum to form the central tendon of the diaphragm and provide a connective tissue scaffolding for muscle cells migrating in on the periphery. The muscles are going to come from somites at the C3 to C5 level, and the mesentery of the esophagus forms the crura of the diaphragm. I should have just started with that. That summarizes that really nicely, but that's what these images are showing. The medial growth of the pleuroperitoneal folds towards the esophagus mesentery, and then the eventual formation of the crura of the diaphragm, and the scaffolding of the muscles coming from somites. Knowing all this, we need to understand what can possibly go wrong. Everything with embryology, remember, we're learning why and how things develop because we want to know what could go wrong and what sort of abnormalities might develop. Here, this is saying congenital diaphragmatic hernias are more common when it comes to some of the malformations we see in embryological development. We've got 1 in 2,000 cases. Most occur when the muscle cells fail to populate a region of the pleuroperitoneal membrane. Remember, the pleuroperitoneal membrane is this blue tissue here, and we're seeing the muscle populate that region. So if the muscle fails to develop, we're going to end up with these like holes. Because they result in a weakening area and subsequent herniations of abdominal organs into the thoracic cavity. That's what this is showing here. Because the muscle failed to develop here, we have an incomplete closure of the thoracic cavity in the chest and the abdominal cavity below. And when you don't have that barrier, you're going to get all these organs shooting up into the chest, and they're putting pressure on the lungs and the heart. Not a good time for the baby. The primary cause for the muscle deficiency appears to be the fibroblasts in the pleuroperitoneal membrane that fail to provide appropriate scaffolding or guidance cues for myoblasts. Okay, finally getting into the GI tract. There's a lot of information, and I apologize it wasn't the most eloquently delivered for you guys. So we have three parts of the gastrointestinal tract, as we've already seen from tail and head folding and lateral folding. So foregut, we saw it already arise as a sort of diverticulum of the endoderm from cranial folding. And this is going to give rise to this sort of region here, which is going to be the stomach, the pancreas, the liver, the gallbladder. I think that's it, but we'll get more into detail as we go along. We have the midgut, which comes from lateral folding. And that is going to be the jejunum, ileum, and the cecum, I think. Again, we'll get into that a little bit more. And then the hindgut at the back end here, which comes from tail folding. Blood supply here, we do have to, it is mentioned in the slides, so we may as well just have a quick peek at that as well. We've got the celiac artery that's feeding the foregut. We have the superior mesenteric artery feeding the midgut. And then we have the inferior mesenteric artery feeding the hindgut down here. Okay. This is outlining which segments of the GI tract come from which section. The foregut is everything from the pharynx, or the mouth, to basically the liver outgrowth. So that's going to be the stomach, the pancreas, the gallbladder, etc. The midgut is going to begin below the liver bud and extend down to the junction of the right 2/3 and left 2/3 of the transverse colon. So we've got, I think it's the sphincter of Oddi. I hope I'm not wrong, but the sphincter where the pancreatic juice and bile are secreted into the duodenum. Everything above that is going to be foregut. Everything below that is going to be midgut. And the midgut is going to last or extend all the way until basically the junction of the transverse colon to the descending colon. A little bit more of the transverse colon is hindgut, but you can roughly think of the transverse into descending colon junction as sort of being the cutoff for the midgut. And then the hindgut is everything else. So the descending colon, the last little bit of the transverse colon, all the way down through the anus. Endoderm is what's going to be lining the gut. And the visceral mesoderm is going to form the stroma. So here I have a nice line representing our entire intestinal system, starting from the oropharyngeal membrane all the way to the cloacal membrane, and the divisions of each. So prior to week 4, the gut tube is closed at both oropharyngeal and cloacal membranes. We still have that 2-layer structure of ectoderm and endoderm. All the glands of the digestive tract are derived from this primitive gut. The glands are going to be stomach, which secretes different things. All the glands in the small intestine, resulting in digestion. The pancreas, the liver has glands in it. All of those things are coming from this primordial digestive tract. Okay, the foregut. Here we have a list of the derivatives, so things that arise from it. We have the primordial mouth, oral cavity, pharynx, tongue, tonsil, salivary glands, and the respiratory system. We've got the esophagus and the stomach, Now it's important to note that the respiratory system and the esophagus both arise from one singular tube because we're going to get into defects of what can happen in a few slides when you have a failure of those two structures to separate. The duodenum proximal to the bile duct. Oh, I did have right. Okay, the sphincter body. And then we've got the liver, the gallbladder, and associated structures, and the pancreas. Now I'm actually going to go back up because I had a little image of this all drawn out. I don't know why I put it way up here. There. This image. Okay. Let's see if I can orient you to what this drawing is. So here we've got the neural tube. This is the developing brain and the spinal cord all the way down to the tail end here. We have the oropharyngeal membrane, the cloacal membrane, and this tube structure all the way throughout the abdominal cavity. And this was foregut by head folding, hindgut by tail folding, midgut by lateral folding. So here we have this initial this first bit here is going to become the esophagus. We have an outpouching here, a diverticulum, that's going to become the lung. So we see like an outpouching. Then we have what's going to become the stomach. Below the stomach, we have the starting of the duodenum, and then we have these two little buds. We have the pancreatic bud to the back and the liver bud to the front. And then as the duodenum continues back, this is going to become the jejunum and the ileum. And then right around this crest here, we're going to see the large intestine. We're going to see the appendix kind of as a little bud here. And then we've got all of the colon, ascending, transverse, descending, and then down to the bottom here, we have the cloaca, which is going to further separate into our urinary system, urogenital system, and the rectum and anus. So all these little bumps all over are going to develop into important things. And here we have the remnant of the yolk sac, and this is the umbilical cord. So we have this diverticulum projecting into the umbilical cord. This should be completely gone before the baby's even born. Oh yeah, and here we see the allantois is going to become the bladder and the reproductive organs. Okay. We're finally making some progress here. Derivatives of the foregut, esophagus, stomach, and duodenum, plus all of this stuff. Except the spleen. The spleen is something else. It doesn't come from foregut. It's going to come from mesoderm, splanchnic mesoderm. But I could be wrong, but we're going to see that near the end of this PowerPoint. Okay, which embryonic layer contributes to the formation of the serous membranes that line the outside of the abdominal organs, lungs, and heart? It's going to be the mesoderm. And again, the splanchnic mesoderm is going to be the serous membrane around the organ. The somatic mesoderm is going to be the serous membrane around the body cavity. It's two, and they fill with serous fluid in between them. The diaphragm develops from the fusion of which of the following structures? Don't know what that is. No, it's not from the spinal cord. These are irrelevant. We know a dermatome is the sensory distribution of nerves. Sclerotome, I don't know what that is. So somites, pleuroperitoneal membrane, and the mesentery of the esophagus is what we're going to see the diaphragm develop from. Because remember that pleuroperitoneal membrane was that structure sort of at the retroperitoneal side of the embryo, and it's growing medially towards the esophagus to form the diaphragm. Okay, remember I said it was important to note that The esophagus and the trachea, or the start of the lungs, both arise from the same tube. So if we have a failure of those tubes to separate, we're going to start to see congenital malformations and we're going to see problems that, from my point of view, seem pretty serious. So we see a partition form between the esophageal tracheal septum, or it's called the esophageal tracheal septum. This is going to become elongated as the heart and lungs grow and descend deeper and deeper. So it's sort of pulling the tissue and elongating it as it goes. The muscular coat of the esophagus is formed by the surrounding splanchnic mesoderm. It is striated in the upper 2/3, innervated by the vagus nerve, and smooth in the lower 1/3, which we've learned in previous lectures. So the upper 2/3 are striated muscle, and the lower 1/3 of the esophagus is going to be smooth muscle. So we have voluntary control basically of the first little bit, but then reflexes take over and smooth muscle kicks in when we swallow. So we can orient you to these pictures. We have the foregut here. We have a little bud forming off of the foregut. This is the respiratory diverticulum. Remember, diverticulum is just a pouch. From the front or ventral view, we see that these are going to become the little lungs here, but there's still an opening between the primitive the primitive trachea to the front and the esophagus to the back. But with time, there's a complete separation between these two structures, which is great because food is supposed to go down into the esophagus and only air should go into our trachea. We all know that unpleasant feeling of swallowing the wrong way. Development of the stomach. So we see a fusiform enlargement of the caudal part of the foregut. So we're still in the foregut, but we're going down, we're moving to the caudal end, we're going to the back. We see a faster growing of the dorsal border. That's this back side. Because the stomach, when we look at it in us, the greater curvature sort of like is to the left side and the lesser curvature is to the medial aspect of the body. But at this point, the stomach isn't oriented to the side like this. It's basically straight down the middle and it's growing in this J shape outwards. So the lesser curvature is facing ventral and the greater curvature is facing dorsal or to the back. Which is what I'm getting to here. The stomach will then rotate 90 degrees so that the anterior border here ends up facing to the medial side of the body, or to the right side, and the greater curvature to the left side. That's what this is showing. So originally we're looking straight on. We have the esophagus, this primitive stomach, also known as a fusiform enlargement. And then it's going to rotate to one side. And as it's rotating, the greater curvature is growing at a faster rate than the lesser curvature. So that's how come we end up with this J-shaped stomach. I'm not going to orient you to the mesenteries because I can't. I didn't spend enough time on this one. Moving on. Here's the picture though. I drew this picture. That's what I already oriented you to. I should have just looked ahead in my slides. We've got the esophagus, the stomach forming. We have these teeny tiny pancreatic bud, liver, gallbladder. These are all things growing off of the tube of the foregut. Yeah, this is just showing as the stomach rotates, we have the mesenteries also rotating. Okay, congenital malformations of the esophagus. Because it starts as one tube that splits into two tubes that must be completely separated from each other based off various function, one for breathing, one for consuming food, we can see problems arise. So we've got three versions of a failure of the esophagus and the trachea to separate and grow properly. Um, the most common cause is because the tracheoesophageal septum doesn't properly develop, or we get a deviation. One of the symptoms of this is going to be polyhydramnios. I'm sure I'm not saying that right, but the accumulation of too much amniotic fluid around the baby. This was one of our quiz questions. And I'll explain why as best I can once I break down each of these three versions. So A is an atresia of the esophagus and the esophagotracheal fistula. So this should be a continuous tube like we see here, but it's not. The esophagus failed to develop completely, and instead we'd have a trachea. So if a baby's drinking fluid, there's nowhere for the fluid to go, like milk, essentially, right? It can't go down to the stomach. It stops and you end up getting vomiting. In this case, the trachea opens up into the esophagus down here. And B, the atresia of the esophagus, the connection between the distal part of the esophagus and trachea is formed by a fibrous cord. So we have a closure. This is just a fibrous cord. In this case, it's open to the trachea, but in this case, it's not open at all. And then in this final picture, we have the proximal and distal part of the esophagus are both connected to the trachea by a narrow canal. So there's a hole right here. So if you're consuming fluid down the esophagus, some of it is going to go into the lungs when it should just keep passing down through the esophagus to the stomach. Oh, I made it nice and easy for us here. I didn't have to go through that. We've got the fistula, that's the first one. The cord, fibrous cord connection is the second one. And connection to the trachea is the third one. Basically, in all three scenarios, we have an incomplete separation of the esophagus and the trachea. So why would we have too much amniotic fluid? Once the oropharyngeal membrane and the cloacal membrane have dissolved and opened up into the mouth and anus, the baby is going to be drinking in amniotic fluid. As it's drinking in that amniotic fluid, the digestive system is going to start pulling that fluid into the blood supply of the baby, much like how when we drink a coffee, we absorb it through our intestines. It goes into our blood system. Once it's in the blood, it's going to be dumped into the placenta and into the mother's circulatory system. So the amnioblasts, the amniotic tissue that forms the amniotic cavity, is constantly secreting new amniotic fluid. And the baby is swallowing that, and a portion of that fluid is getting dumped into the mother's circulatory system for excretion. So you have new fluid being made and old fluid being dumped out. So we have a nice flow of fluid. We're not accumulating too much. In this case, because we are not able to swallow, the baby's not able to swallow any amniotic fluid and therefore not absorb it and therefore not dump it into the mother for excretion, the amniotic fluid is accumulating. The amnioblasts, because they're always producing more amniotic fluid, is creating more of a supply than we can get rid of. Hopefully that makes sense. Okay, congenital malformations of the stomach. We just did the esophagus, now we're moving down. We can basically have a similar issue where we just don't get a complete opening of the gastrointestinal tract. So we have a pyloric stenosis. Remember, the pyloric sphincter separates the stomach from the duodenum. In this case, it's way overdeveloped. So we're going to have a similar issue. The baby is swallowing amniotic fluid, but it can't go down to the duodenum to be absorbed. So we get the same outcome, polyhydramnios, the buildup of amniotic fluid. We're also going to see projectile vomiting in the baby once it's born and it's trying to drink, because all that milk is going to be coming and sitting in the stomach. And a baby's stomach is teeny, teeny, tiny. It doesn't have a lot of space in it. So as soon as the stomach reaches capacity, it's going to come shooting back out. Here's the logic. The alimentary canal absorbs amniotic fluid and the placenta dumps what's absorbed into mom. This decrease in amniotic fluid so it can be continually replaced. Blockage of the stomach or the esophagus, as we saw with the esophageal atresia, It's going to result in no ability to dump excess amniotic fluid into them, so we get polyhydramnios. Okay, the development of the duodenum, moving on. Development from the caudal part of the foregut. So again, we're moving caudal towards the end of the foregut. We're not at the mouth anymore. We've descended down past the esophagus and lungs, past the stomach. Now we're hitting the duodenum. And it is just proximal to the midgut. So we're almost at the end of the foregut at this point. The junction of the two parts is directly distal to the origin of the bile duct, the sphincter of Oddi, as we've already said. That's sort of our cutoff point between foregut and midgut. The duodenum is going to grow rapidly and form a C-shaped loop. With rotation of the stomach, because remember we saw it rotate 90 degrees so that it goes from being sort of looking at the stomach was facing you this way, it's rotated to the side. So we have our greater curvature to the left side and the lesser curvature to the midline or right side. This rotation is going to push the duodenum further back. So it's going to become a retroperitoneal organ. So it's basically going to be touching the back wall of the abdominal cavity. Because it is a derivative of both foregut and midgut, it is supplied by two different arteries. We're going to have branches of the celiac artery, which is for the foregut, and the superior mesenteric artery, which is for the midgut. This is showing you that rotation, how as the stomach is rotating, the duodenum here is rotating back towards the back wall of the abdomen. This is actually a good picture. This is the ventral side, this is the dorsal side, so you can see the stomach is sort of in this plane here, but as things are growing and growing, things are rotating to the side. Okay, we're going to look at something called canalization at this point. So we have the foregut as a tube at this point because of lateral folding. But because everything is growing so rapidly, we're going to see tissue growth that basically completely blocks that tube in the middle. The way I envision this happening is like you have this teeny tiny hole, but the tissue is proliferating so fast that hole gets plugged up with new tissue. But then as the embryo and baby continues to grow, that hole in the middle reopens. That's called recanalization. And the lumen is going to reopen. So the epithelial cells, they're proliferating so rapidly that they end up obliterating the lumen of the duodenum. That's what this is showing here. All this endoderm in the middle forms what's called an epithelial plug at week 4. So this hole, this tube isn't a tube anymore. There's too much tissue covering it. Nothing can pass through. But recanalization is the process of reopening that lumen. So here we see the epithelial plug. As the embryo grows, we're getting some loss of tissue in the middle here. It's called partial recanalization. And then with a little bit more time, the lumen reforms. And now you can see we have all these tiny like microvilli structures that we know are really important for digestion. I'm just trying to break down my own notes because I wrote these back in week 1. The distal foregut and the proximal midgut form the duodenum. Endoderm lines the duodenum. Splanchnic and visceral mesoderm equal the connective tissue and the muscle. Right, the mesoderm is going to become the connective tissue and the muscle of the intestines. At week 6, the endoderm proliferates and blocks the lumen, which is this epithelial plug. The lumen is obliterated. There's no hole or passageway through the tube anymore. If development stalls at this point, the lumen is going to remain closed, which is going to give a duodenal stenosis, which can be partial, or a duodenal atresia, which is a complete blockage. By week 8, this tube should recanalize, epithelial cells die off, apoptosis. We get vacuoles or holes in the epithelial plug that coalesce to reform the lumen. Okay, so just like with the stomach and the esophagus, we can get an atresia or like a blockage. That's referred to as a duodenal stenosis, partial occlusion of the duodenal lumen caused by incomplete canalization versus a duodenal atresia is a complete occlusion of the lumen. That's important to note. A stenosis is just a partial closure. The atresia is a complete closure. If you can remember that too, the esophageal atresia a few slides back is like, boom, there's absolutely no partial connection at all. Atresia is just like hard stop. There's no passage through the tube when there should be. God, I hope for you guys that this is making sense. So when we have a duodenal atresia, we see distension of the epigastric region in infants, so the stomach and the esophagus, and vomiting will begin within a few hours after birth. The vomit in this case is going to contain bile because the blockage is happening lower on in the GIT. We're going to see bile is starting to mix a little bit here because we have our sphincter of Oddi connected somewhere in here, so we're going to have bile. That's a key differentiating feature. If we have a pyloric stenosis or we have the esophageal atresia, when the baby vomits back up milk, it's going to be bile free because the closure is happening too proximal in the GIT for bile to even make it in the mix. But with a duodenal stenosis, bile is likely going to have a chance to mix in with the milk before you end up seeing vomiting. So bile denotes a duodenal stenosis. No bile is going to be a problem further up with the stomach or the esophagus. Same issue here, polyhydramnios, because of the reasons I've already been over. The amniotic fluid cannot be absorbed into the baby and therefore cannot be dumped through the placenta into the mother to be excreted. Okay, liver and gallbladder. We see a hepatic diverticulum as a ventral outgrowth from the distal or caudal part of the foregut. This is going to give rise to the liver, the gallbladder, and the bile duct. So we're at the foregut. We haven't reached the midgut left. We see this tiny little diverticulum that's going to become the liver and gallbladder. The cranial part of the liver grows superiorly, grows upwards, and meets the septum transversum, which we've already discussed as being the future diaphragm. The liver bud then forms parenchyma of the liver, which is the functioning liver cells. The other cells we know that reside in the liver, such as the Kupffer cells and hematopoietic tissue, are derived from the mesenchyme in the septum transversum. So the liver bud arises from the foregut, and the liver bud is the parenchyma tissue. The other tissue, the other associated liver tissue, is going to come from the mesenchyme of the septum transversum. So I feel like that's an important differentiation. It's like what tissue in the liver comes from where. The parenchyma is going to be coming from the foregut, whereas the Kupffer cells, the immune cells, and the hematopoietic tissue are going to come from mesenchyme of the septum, or the diaphragm is essentially what it's going to become. The liver is a huge mass at this point. It's 10% of the total weight of the baby. So like huge, because the liver is so important, right? In processing nutrients. it makes sense that you would want to have this structure really developed early on as the fetus is starting to, well, it has been the whole time, but the fetus is getting nutrients from the mother. So it needs to be able to start like making enzymes and dealing with nutrients in appropriate ways, etc. The caudal part of the hepatic diverticulum is going to become the gallbladder. So the cranial part becomes the liver bud, which becomes the liver. The caudal part, the tail part, becomes the gallbladder, which we see here. This is the cranial part to the top, the caudal part to the bottom, gallbladder. The stalk of the liver bud is going to form the cystic duct and the common bile duct. This is a summary of what I said. Like, know this. If there's anything from this slide you take away, it's this. Where the tissue comes from of the liver. Okay, another atresia. Remember, atresia is a full blockage of a canal or a tube so that fluid or secretions or whatever is not able to pass through it when it should. So remember, the canalization was the closure of the tube because you have proliferating endoderm cells. So we have a failure of recanalization and extrahepatic biliary atresia. That's one problem that we can see in fetal development. The other is we can actually get a duplication of the gallbladder, so we can have two. I don't know what the clinical significance of that is, if it's a problem or not. Okay, the pancreas. We're almost through foregut. So we have a liver bud. We also have a pancreatic bud that will arise from the caudal part of the foregut. Due to the rotation of the duodenum as the stomach is turning, the ventral bud is, it's originally in the front, but with that rotation, it's taken from the front and it's moved all the way to the back, along with the bile duct. And we actually see two buds initially. So here we have the dorsal pancreatic bud and the ventral pancreatic bud. And as this rotates, this stays pretty anchored, but this part here is going to rotate back to meet up with the pancreas and fuse together to create the entire organ. The ventral bud becomes the head of the pancreas and the dorsal forms the rest. Here we're seeing that rotation. We have the ventral bud and the dorsal bud, and this is rotating this way, and they're going to meet together and they're going to form the pancreas. And then we also have our nice little duct system here into the duodenum. Bile duct coming down, the pancreatic duct meeting it, and the sphincter of Oddi. Okay, pancreatic malformations. During the process of rotating, if rotation happens incorrectly, the anterior bud can sometimes end up wrapping around the duodenum. Sorry. Yeah. So we end up with this like ring around the duodenum, which is problematic because I'm sure you can guess why it's problematic. You're not able to properly get food passing through. I'm unclear from the slides if this like kind of acts like a complete blockage of the duodenum into the jejunum or if it's like partial. We also can see accessory pancreatic tissue sort of moving where it shouldn't be. So because we have these two little buds and because this bud has to move, sometimes this tissue migrates in places that it shouldn't be. So you can see pancreatic tissue in places like the stomach, the duodenum, or the ileal diverticulum. Remember the ileal diverticulum is Meckel's diverticulum. It's that sort of tube structure that used to be the yolk sac that should be reintegrated into the body, but fails to do so in development. Okay, the spleen comes from mesenchymal cells. So remember earlier on I said that most of the organs liver, stomach, duodenum, pancreas, they all arise from the foregut tissue. But the spleen is different because it is derived from a mass of mesenchymal cells coming from the splanchnic mesoderm. What happens in the formation of the spleen is you start with all these little lobules of tissue. So the spleen develops as many small lobes that eventually grow together and fuse to make the organ. I have my little tissue reminder here. We've got somatic mesoderm here, splanchnic mesoderm here, to the bottom. Okay, midgut. I think I'm just going to take another little break here with recording. Okay, I'm back from a little break. Let's continue. Okay, so we've wrapped up foregut and all of the sort of concerns with development with all the different atresias or improper development or recanalization of the alimentary canal. But the midgut, we're gonna now focus on. So we've got the small intestine, including most of the duodenum. Again, anything past the sphincter of Oddi is going to be from the midgut. We've got the cecum down here, that sort of first part of the ascending colon, and the right 2/3 of the transverse colon. So it comes all the way across. It probably stops right about here, which is relevant in innervation. So we've seen that before a few times, that this part of the GI tract is separately innervated than the descending colon. The midgut is suspended from the dorsal abdominal wall by elongated mesentery and is supplied by the superior mesenteric artery. The celiac artery is for the foregut, and the inferior mesenteric artery is for the hindgut. Okay, the midgut loop. So the formation of the midgut loop, a ventral U-shaped loop with a cranial and caudal limb, appears due to the elongation of the midgut. So here we have the cranial side and the caudal side. This is remnants of the yolk sac or primary umbilical vesicle, which will potentially lead to a diverticulum if it doesn't close properly, known as Meckel's diverticulitis if it gets inflamed. The midgut will end up looping into the umbilical cord as it grows because there's not enough room in the abdomen for the rapidly growing midgut. This is known as a physiological umbilical hernia. Okay, rotation. I actually have a bit of a video that I found on YouTube that explains this so much better than what we can figure out with all these photos. But we'll go through the text first and then I'll switch screens to show you guys that. So throughout development, the midgut loop is going to end up rotating counterclockwise on 2 occasions. The first rotation is a simple 90-degree rotation where we have it's sort of along this axis, and then it rotates 90 degrees to be more horizontal. That's what this is showing down here. It starts vertical and then it rotates to become flatter and more horizontal. The second rotation is going to be a 180-degree rotation that occurs while the physiological umbilical hernia comes back into the body. So I'll just say that again. The 180-degree rotation occurs as the physiologic umbilical hernia is resorbed back into the abdomen. And this is going to give rise to the structure of the colon as we know it, that N shape. So it's rising, ascending, transversing, and descending. The rotation occurs around the axis of the superior mesenteric artery. This is going to be occurring during the 10th week of development as the intestines come back into the abdomen and the physiologic midgut hernia disappears or is reduced. The order that this happens in is that the small intestine is the first part to come back into the abdomen, and then the large intestine comes after. This is significant because the large intestine, as it's coming in last, certain aspects of the large intestine are going to be more ventral than the rest of the alimentary canal. And in this process of the large intestine coming in, it's going to push other structures backwards as it comes over top. And those structures are going to fuse partially to the retroperitoneal canal, and they're not going to be like free floating, and they're not going to have the same mesentery structure. So let's look at a quick video. Okay. So here's what we're seeing. We're seeing um, the mid gut pushing out into the umbilical cord. We've got the caudal region, or sorry, the cranial region, my bad. Um, and the sort of um, caudal region. Apologies on the terminology escaping me right now. So that's what this region is. Here's the superior mesenteric artery. So it's projected out into the umbilical cord. And then we're going to see the first 90-degree rotation. At this point, you'll see this little outpouch in here. This is going to become the appendix and the cecum. And next, what's happening is the previously cranial region, it's not cranial anymore because it's level with the caudal region, is sort of kinking up and the small intestine are developing. So we're going to see the portion of the duodenum past the sphincter of Oddi. We're going to see the mid region, the jejunum, and then we're going to see the most distal part, the ileum. Sorry about that. Okay, so that's the first rotation. And here's the second rotation happening. As this is happening, we're seeing the small intestine re-enter the abdominal cavity first, and then the large intestine is following and it's completing its rotation. Ooh, I want to pause there. Okay, if we pause here, we'll see the large intestine has come in last and it's pushed some structures backwards. So we see the duodenum is pushed back. This is going to become part of the retroperitoneal membrane. So it's not going to be free floating with mesentery. The ileum and the jejunum and the ileum are going to be more free floating. They're going to maintain that double mesentery layer. So they're going to be able to like float around, move around a little bit more. The ascending colon is also going to be retroperitoneal. The transverse colon is not retroperitoneal because it's in front of everything. And the descending colon is also retroperitoneal. I'm just going to play that for you guys one more time. We get the herniation, first rotation of 90 degrees, further development of structures, and the second rotation at 180 degrees, which brings the large intestine in last, forming the structure of our abdominal cavity as we know it now. Oh, okay. Okay, so fixation of the intestine to their final position. So we see that rotation of the stomach and the duodenum, which brings the duodenum and the pancreas to the right side of the abdominal cavity. So if it's facing forward, it rotates to the side and we get this J shape. These structures are pressed to the posterior abdominal wall as the colon re-enters the abdominal cavity. The colon sits on top or over top of the duodenum and the pancreas. The adjacent layers of the peritoneum will fuse and subsequently disappear. I already mentioned this. In the process of being pressed into the posterior abdominal wall, the peritoneum will fuse into one layer, so we lose that double mesentery. Most of the duodenum and the pancreas, with the exception of the pancreatic tail, become retroperitoneal. With this mechanism, pressing some parts of the midgut and hindgut to the posterior abdominal wall, the ascending colon and descending colon also become retroperitoneal. The jejunum and the ileum, as well as the transverse colon and sigmoid colon, retain their mesentery and take their intra-abdominal final position. They are free floating because they have the double mesentery. Here we see the greater omentum for the stomach, and then down here we see that double layer of mesentery along the distal part of the small intestine. That's what this is here too. So here there's no double mesentery. The pancreas and the duodenum, they're anchored flat against the back wall, the retroperitoneal cavity, but the other parts of the intestine, they're kind of more free floating. They can sort of move around a little bit more, which is good. We don't want anything we could get a bowel obstruction if these things get stuck or anchored and they get blood supply cut off. Here is a list. Summary on the intestinal fixation. Okay, there we go. During midgut rotation, certain aspects of the GI tract get pushed against the posterior abdominal wall. This results in the fusion of adjacent layers of peritoneum and the disappearance of a double mesentery. This results in the anchoring of the GI tract to the retroperitoneal cavity, aka the posterior abdominal wall. So we have the structures that are anchored. They've lost their double mesentery because that has fused to the back wall of the abdomen. We have the duodenum, the pancreas, the ascending colon, and the descending colon. The rest of the structures of the alimentary canal remain sort of free floating in the abdominal cavity because their double mesentery remains intact as they were not pushed against the retroperitoneal wall during midgut rotation. So we have the stomach, the tail of the pancreas, the jejunum, the ileum, transverse colon, and the sigmoid colon. Development of the cecum and the appendix. The primordium of the cecum and the appendix, known as the cecal diverticulum, appears as a swelling on the midgut after the first 90-degree rotation, which is shown here. So we went from that vertical axis to that horizontal axis. And this part, this was the cranial loop or the cranial end, and this was the caudal end. We see this diverticulum appear. And then as the diverticulum descends and the ascending colon, cecum, and appendix form, as the second 180-degree rotation occurs, the diverticulum is going to descend lower as everything is sort of moving its way back into the abdomen. At the same time, the ascending colon, the cecum, and the appendix are forming. Remember, we saw that in that rotation. As things start rotating, things elongate and they end up getting anchored in their final position in the abdomen. The cecum and the appendix continue to grow after birth, and the appendix will take its final position after birth, which, if we remember, there's sort of various positions that it can end up, which may or may not increase the likelihood of appendicitis. Abnormalities that can be visualized of the midgut are going to have to do with abnormalities of gut rotation. So we can get congenital omphalocele, which is persistence of the herniation of the intestinal loop in the proximal part of the umbilical cord. Because the intestines had to push out into the umbilical cord to have enough space to grow and elongate, if they don't end up coming back inside the body, you end up with this pouch outside of the body that has all the small intestine inside of it. That's called the omphalocele. We can also get gastroschisis. This is less about the intestines failing to come back inside the abdomen, and it's more about a failure for the abdominal wall in lateral folding to completely close in the 4th week of fetal development. This means that the viscera or the abdominal organs will protrude into the amniotic cavity. Poor little baby. A less severe version of that is the umbilical hernia. The organs in this case mostly do go back into the abdomen during rotation as they're supposed to, but there's a failure in the closure of that sort of yolk sac region. So the intestines can't herniate through the imperfectly closed umbilicus. So everything moved back inside. It's just that the umbilicus region, that central region of the abdomen, didn't continue knitting closed. So there's like an issue with the muscle layer, perhaps. Connective tissue structure could be compromised, thus leading to a hernia. Okay, Meckel's diverticulum. I brought this up multiple times. Sometimes what can happen, the proximal portion of the yolk sac remains and forms the diverticulum. So that's really illustrated here. We see the primordium of the alimentary canal. We don't see the stomach yet. We don't see the liver or the pancreas. But we do see this umbilical vesicle, the yolk stalk or yolk sac. This eventually shrivels down into nothing. So ideally, as the alimentary canal develops, everything from here on disappears. So you get this perfect closed loop. But that doesn't always happen, and you end up with this little remnant here. The significance of this is that this diverticulum can sometimes become problematic and inflamed from something like a fecalith, leading to symptoms that are very similar to appendicitis. I think the clinical differentiating feature here is that this appears in the lower left quadrant, while appendicitis appears on the right side. The wall of the diverticulum may even contain small patches of gastric and pancreatic tissue. Remember earlier we talked about one thing that can happen with the pancreas as it's migrating to have the anterior and posterior buds form together, is you can have little bits of tissue that are just like, they go AWOL and they're like, I'm gonna go way over here in this part of the alimentary canal instead. So in this case, you might see some of that happening. So you might get, if the tissue's functioning, you might end up having enzymatic secretion happening from pancreatic tissue. The gastric mucosa in this region can often secrete acid, leading to ulcerations and bleeding. So if we have gastric tissue and pancreatic tissue in this little diverticulum, we're going to be getting hydrochloric acid secretion. We're going to be getting all those pancreatic juices potentially being secreted, which, if not done properly in a controlled way, can lead to self-digestion, hence ulcerations and bleeding. Okay, what about an omphaloenteric fistula? So what's the difference between a fistula and a diverticulum? A diverticulum is a pouch. So if we have the alimentary canal, a diverticulum is going to be an outpouching like this. A fistula would be an outpouching, except it opens at one end. So in this case, it's not the worst thing. You just run the compromise of things getting stuck in here, but they can go in and they can come out, and they're not going to enter the abdominal cavity or wherever. In the case of a fistula, it's an open tube. So you could potentially have food coming down, or not food at this point, but you know what I mean. You could have the things you're digesting come out into the open. And think about how much can get into your body at this point too. Like all the different bacteria that could be coming into the abdomen, they're invading the alimentary canal, et cetera, et cetera. So this results from the persistence of the entire intra-abdominal portion of the yolk sac. Here we see that illustrated. It's a complete hole to the outside world. Here I have the definition of a fistula for you: abnormal connection or passage between two epithelial surfaces, a tunnel that should not exist. You see that here too. They've obviously taken this part of the intestine out. You see the umbilical vesicle or the yolk sac with a hole on the other end that would be facing the outside world. Okay, quiz. During the embryonic development of the stomach, which of the following statements is correct regarding its rotation? The stomach rotates 180 degrees clockwise around its long axis. No, we know that it only does a quarter turn. So it's only a 90-degree clockwise rotation, which is why B is the right answer. So if we break this question down, C, so if the stomach is facing, the best way to illustrate this. I actually don't have anything that I can think of. Basically, the stomach is going to rotate with the lesser curvature facing away from you. That lesser curvature is going to rotate to the right. So this is saying that the ventral border, the anterior border, the lesser curvature is moving to the left. But if you think about your stomach and your body, it's curving in this direction. We can see my abdomen. So if the curvature is facing frontwards, hold on, it's facing frontwards, this curvature, the lesser curvature, the greater curvature of the back of my head, it's going to rotate to the right. Same thing with D. The stomach rotation involves the left surface moving posteriorly. No, we know it moves anterior. Try and visualize how your stomach sits in your head now, and then you should be able to answer a question like this if it comes up. I'm gonna skip this. Okay, hind gut. So we have less than 10 slides left. The left third of the transverse colon is the beginning of the hindgut. We have the descending colon, sigmoid colon, the rectum, and the superior part of the anal canal, all deriving from the hindgut. The epithelium of the urinary bladder and most of the urethra also arises here. And everything in this region is supplied by the inferior mesenteric artery, with the exception of the bladder and the urethra. Due to the midgut rotation and the returning of the intestinal loop into the abdomen, the descending colon becomes retroperitoneal, and the sigmoid, this region, will retain its mesentery. So this part is not retroperitoneal. I'm going to see if I have that on my list. I do, sigmoid colon. Okay, the cloaca. So we've been seeing the cloaca for a long time now. It arose pretty early on in embryological development. This is the terminal dilated portion of the hindgut. So this is the part of the hindgut that touches the cloacal membrane. Just like we have a membrane up here, we also have one at the bottom too. The mouth primordium and the anal primordium. The cloaca membrane is composed of endoderm and ectoderm. And the ectoderm is part of something known as the proctodeum, or the anal pit. The anal pit is sort of this depression right here that pushes inward. If you're having a hard time remembering proctodeum, remember procto is the Latin word for anus or rectum, and nobody wants to go to the proctologist. So procto, just remember that is your connection to anus or rectum. Okay, partitioning of the cloaca. How do we go from a single tube in our pelvic bowl to having multiple different structures? Because we have a urogenital system and we have our rectal system as well. So what happens to create a separation or a partition of the cloaca, we are going to see the development of the urorectal septum, which is a wedge of mesenchyme that divides the cloaca into a ventral and a dorsal part. The ventral part is going to become the urogenital system, and the dorsal part is going to become the rectum, which makes sense. If you think about your own anatomy, think about your pelvic bowl. Your bladder sits ventral or in front of your colon. So ventral is bladder, dorsal is colon. And of course, we also have our genital system as well. The urorectal septum will fuse to the cloacal membrane. So here we see the septum coming down, down, down. It's going towards the cloacal membrane where it will eventually fuse completely. We've already talked about this. The ectodermal depression that's near the anus is known as the proctodeum or anal pit. So the cloacal membrane at this point is divided. The part that is covering the rectum is the proctodeum. This will eventually rupture and it will become able to communicate with the amniotic cavity, which makes sense. We know we have a sphincter there. Zooming into the anal canal, we talked about how most of it arises from the foregut, but there is a little tiny bit of it that arises from the ectoderm, or the outer layer, skin essentially. The inferior 1/3 is the part that comes from the ectoderm, the skin, so that sort of folds inward and upwards, and it ends up meeting the mesoderm that develops the foregut. Sorry, hindgut. I meant to say hindgut. There is a line, the pectinate line, that demarcates the border between these two tissue types since they arise from different origins. There is a difference in blood supply, nerve supply, venous supply, and lymphatic drainage of these two parts. The clinical importance of these differences can be considered in clinical cases. I know that above the pectinate line, we have way less sensation because this tissue is not like skin. Skin is full of sensory nerve endings. So that means that the distal part of the pectinate line is going to be way more sensitive. So if you have a hemorrhoid in this region, really painful. Hemorrhoid up here, not so much. The upper 2/3, autonomic nervous system. The lower, the pudendal nerve of the somatic nervous system. Again, that's why this part, we feel so much more sensitive in that region. We've got the superior and inferior rectal arteries. We've got the superior rectal vein and the inferior rectal vein. And then we've got inferior mesenteric lymph nodes and the inguinal lymph nodes, respectively. I already talked about that. Internal hemorrhoids are not going to be as painful because they're above the pectinate line. External hemorrhoids are covered by skin that contains pain receptors. Here's the difference. Not really that painful, starting to get painful because it's pushing on the tissue down here, and then this one would be pretty painful. Okay, we have a potential pathology coming from embryo development. So because the colon is supplied by the autonomic nervous system, if we have a failure of these autonomic ganglion cells to develop in the myenteric plexus, we'll get like a sensory feedback error. So there'll be no nerves to sense that there is stuff to be voided in the colon, which develops into a problem known as congenital megacolon. So we don't want that. Okay, a few summarizing things about the role of amniotic fluid. It's going to protect the fetus and act as a cushion. It's going to help protect the fetus from infectious agent due to its inherent antibacterial property. It serves as a reservoir of fluid and nutrient for the fetus, containing proteins, electrolytes, immunoglobulins, vitamins, all from the mother. It's going to provide fluid and space and growth factor to allow normal development and growth of fetal organs such as the musculoskeletal system, gastrointestinal system, and pulmonary system. Clinicians can use amniotic fluid as a tool to monitor the progression of pregnancy and predict fetal outcomes. I don't know what this procedure is called. Phlebotomy of the amniotic fluid, I'm not sure. And then one of the main problems we've seen with amniotic fluid is polyhydramnios, which is where we have too much. Try and think back to what caused those. Because if there's a blockage in the alimentary canal at some place that prevents fluid from passing through the alimentary canal, we're not able to have excess amniotic fluid get dumped into the mother's circulatory system for excretion. And then oligohydramnios is just not enough production of amniotic fluid. And there we go, 66 slides. I hope this is helpful.